Welcome back to Codex. Our speaker today is Sarah Tymochko from UCLA. Dr. Tymochko is an expert in network science and topological data analysis. Today, she'll tell us about applications of topological data analysis to resource coverage. Take it away, Sarah.
Thank you so much, and thank you for the invitation to speak. I made a slight modification of my title here, still talking about topological data analysis, but more generally to social systems. So the first part of my talk will be the same. I'll be talking about resource coverage, where we're thinking about coverage of parks in the city of Chicago. But then I want to talk about some, I think, fun work that some undergraduate students of mine did on looking at patterns in math faculty hiring this past summer. So I think it's a fun little interesting use of TDA that we'll get to at the end. So my work primarily focuses on topological data analysis, where we can look for these topological shapes that appear in data. So this is sort of a standard collection of different shapes or manifolds that you might see studying in topology, but where we have them as collections of points rather than as some nice smooth shape. So standard topological techniques might not or are not useful in the context of discrete data, but with some modifications, we can use these to study a lot of different things. So the idea today is to think about the shape of data in the context of spatial data for the most part. So if we look at the city of Chicago, all of these orange points are, I believe, COVID test centers back from like 2021, maybe. But we can see that these are not necessarily equally distributed around the city. There are holes that you can physically see where there are no orange points or no COVID test centers. So we can physically see that there's some inequity in how these places are distributed. And the goal is to use TDA to study how can we capture this in a more meaningful way than looking at the map and saying, yes, I see there's holes. So briefly, I will introduce TDA in like one or two slides. Then, like I said, we'll talk about this application to resource coverage and patterns in faculty hiring. So the main tool that we'll use from topological data analysis is persistent homology. The way that this works is that you have some sort of space that is increasing, it's growing. So you're adding new pieces to your space and seeing how does the topological features change as you do this. So in this example here, at the very beginning, we have 4 points that are all disjoint. Then at the next step, we've added some edges connecting them, added another edge, and added all of these individual pieces. And so persistent homology keeps track of when do topological features appear and disappear, and when do they merge into one. And this information is represented in a persistence diagram. So the birth time here is going to be what is the first one of these, the sequence of simplicial complexes where we see a topological feature appear. And so this point here that's born at time 0 and then dies at time 1 corresponds to the fact that we have 4 different connected components at this starting point. And then one step later at time 1, we have now connected all of them into one connected component. So 3 of those components that were previously separate have now died since they've merged into another existing component. Then we have a cycle that's born at time 2. So once this final edge is added in and we can outline this, this cycle here, we have that circular feature is born. And then it dies at 4 when this last piece of the triangle is added in. So it still exists in the middle here, it's just gotten a little bit smaller and then dies at the end. And the last point here, this point at infinity, corresponds to the fact that there's some connected component that started at the very beginning and is going to last forever. So if you're never removing simplices, you're never going to have less than one component once you have that everything is fully connected. So you have this one point that dies at infinity or never dies. And one important feature that we can look at is what's called a death simplex. And so this is the last piece that's added in that kills a feature. So for zero-dimensional features, that would be like an edge being added in. In 1D, it's, for example, that triangle that gets added in the last step that fills in that hole. So we would consider that depth simplex as sort of the last piece of the hole that is still existing. And in the context of coverage, that might mean something like the place that has least access to whatever resource we're considering. And one nice thing about topological data analysis is it can be applied to really any type of data, as long as you have some way of measuring a notion of distance. And so we can also look at image data where you're looking at sub-level sets, or look at what does the image look like if we only include certain values. So if I only included up to, say, 0.2, then I might only have these dark purple regions. And as I were to increase that threshold, you start adding more and more features. And you can see the same sort of idea of connected components appearing, merging, and disappearing, and holes that are forming, and then eventually filling in. And lastly, another common application or a common data that we work with is networks, where you can use something like a shortest path distance or a weighted shortest path distance and start by adding in all of the nodes to begin with, and then all of the edges where you can get between those nodes in one jump. So you just get back the graph, and then all of the edges where you can get there in 2 jumps and the corresponding triangles and so on. So we can capture this notion of shape in networks as well. Then the last example here, so this is, again, looking at point cloud data where we just have points in space. And we can look at the weighted or just the Vietoris-Rips complex, where we start growing a ball around each point. And once those balls intersect, you add an edge between them. Once you have 3 edges added, you fill in that triangle, and so on. So all of these have some idea of the fact that there's 2 sort of circular features underlying them. And in any type of data, we can capture this in the persistence diagram. So this idea of the sub-level set filtration is primarily what we'll use. But first, the previous work is using this Vietoris-Rips filtration. So this work was originally motivated back in 2020 after there were issues in people accessing polling sites. So some work by Abby Hickok and several others from UCLA, they wrote this paper where they were looking at using persistent homology to access to polling sites. And so briefly to talk about what they did and how our work builds on it, what they did was consider distance between polling sites, but rather than thinking about physical distance, think of it in terms of travel time. So now you're adding vertices corresponding to each polling site, and then you're adding an edge between them once you get to the travel time it takes to get between them. So rather than looking at just holes and coverage you can see from looking at a map, this is also taking into consideration that people may walk, take the bus, drive, and you may have to wait. When you get to the polling site, you have to wait in line to vote. So they incorporated all of this to try and see how can you study this coverage where you're picking up features that you can't just see by looking at the map. And some initial results of theirs. So these are the persistence diagrams corresponding to the city of Atlanta and the city of Chicago. And so there are slightly different distributions in terms of the death times. So that would be when does a cycle or a hole get filled in so that everyone in that region can then have access to a polling site in that time. So we can see that, for example, in Atlanta, there was at least one hole that you needed, or sorry, these are the blue or the one-dimensional holes here. So there's these 2 holes that did not die until, say, 100 or 120 minutes. So it took people 2 hours to vote for the people who lived in that vicinity, whereas in Chicago, there was 1 at 100, but in general, they sort of tend to be a little bit lower here. And we can look at these death simplices that I mentioned. So on the left is the death simplices for Atlanta, and the right is the death simplices for Chicago. And it's colored based on that death time. And so here there's this region where anyone who lived in this area, it could take them up to 130 minutes to be able to vote. So this gives some sort of a visual representation of where these regions are, where the people live who have the most difficulty getting access to polling sites, and could be used to sort of determine where might be a good place to put another polling site, or to have more polling machines or more staff or something to speed up the process. And so a brief cautionary tale. So this is the persistence diagram for looking at New York City. And you can see there's these very persistent polls here that don't die for until like over 120 minutes, which sounds really bad. But when we look at the physical space where those people would have to live, this is the city and this is water. So if you were to have even though there's a hole here between these different parts of New York City, we wouldn't actually necessarily want to consider this a hole, since the majority of the space is just water where no one lives. So with this geographic data, you do have to be a little bit careful that there is complicating underlying geography that makes it not as easy to just take the results as fixed. You have to really look back and see what the space is representing, what these holes are representing. Okay, so now looking at parks, one thing that we might want to look at, so this is the outline of Chicago here, and it's a little bit hard to see, but these red boxes, those are outlines of parks in Chicago. And the color here is based on the distance to the nearest park. The purple areas are the ones that are really close to a nearby park, and the yellow or bright areas are the ones that are far away from a nearby park. So you might think that this is sort of the end of the story. If we're just thinking about the geographic distribution of these parks, then we already know, based on this information, who has the hardest time getting access to their closest park, who's furthest away. But there's some details and some nuance with parks that we wanted to take into consideration. So this is one park in Chicago. This is Grant Park. It's 319 acres. It has an art institute, an aquarium, basketball and tennis courts, anything you could want in a park. And this is Park 432 in Chicago as well. And so that previous idea of looking at just what's your distance to your closest park would treat these two things as the same, which I think we can all agree these having access to Grant Park is not the same as having access to this small patch of grass. So we want to adjust the approach for looking at polling sites, but rather than thinking about time and transportation time, we're going to introduce a notion of quality here. So that's sort of the additional complicating factor where we can't just look at the map. Okay. So, right, so this is a case study of looking at access to parks in Chicago. There was a lot of news about this during the pandemic of how having access to parks and green space is vital, and why isn't there more? If you've been to Los Angeles, you probably know that this is a particularly strong example of a place that has a lack of parks. So it's a bit near and dear to all of our hearts. So this is joint work with Abby Hickok, Jerry Liu, Jill Grindstaff, and Mason Porter. The first question that we had to think about is what defines a good park? So one definition could just be the size or the number of acres. So having access to a large park might be better than having access to a small park. Here, this is Chicago, and so this is right along Lake Michigan. And they have these really large parks that are right along the water, and then much smaller ones more inland. Another thing we thought about when deciding what's a good park is what do people think is a good park? And so we looked at Google reviews for parks, which is something that one might not think to review a park on Google reviews, but some people do. And this gives a sort of human idea of what do people think of this park? Do people like visiting here? Do people not like visiting here? So it has, we have one that's sort of just based on the geography of the park and one that's more based on the human perspective of what makes a good park. Okay. So also, please, anyone feel free to stop me with questions along the way. Um, but right, so here, the first thing we can think about is if I live in some neighborhood of Chicago and I'm willing to walk a fixed distance, say I'm willing to walk R kilometers, then how much total quality of park do I have access to? So this could be if I'm willing to walk 1 kilometer, how many acres of parks is in a 1 kilometer radius of where I live? And if we do that for every block or every census block in Chicago and say how much do I have access to if I'm willing to walk 0 kilometers? Well, no one has access to any parks. But once you start increasing that distance, you see who has access to the most acreage of parks. And here you get the effect of those really large parks along the lake, where anyone who lives near to the lake is going to have better access or have more access, just since those parks are so overwhelmingly large compared to the others. But you can see other small spots appearing where these folks here would now have better access to parks if they're willing to walk a little further than, say, people over here who still don't have hardly any access. And we can look at the same thing for Google reviews, where now, since the quality was a bit more scattered through the city, we get this sort of patchy effect where nearby all of these parks that I guess were considered to be good, you get these little circles appearing for who has quality nearby, whereas over here, there's still no real high quality parks to have access to. So visually, we can see that there are discrepancies in terms of who has access to any park and who has access to a good quantity or quality of park. But of course, this is all just very qualitative looking at these animations. So how can we capture this more mathematically? So the first thing we can look at is the sub-level set, where we consider any census blocks in Chicago where, say, within 2,000 meters of that census block, you have access to 0 acres of parks. So anyone who lives in any of these small little blue regions, they can walk 2 kilometers in any direction from their house and not have access to a single acre of parks. We could then increase that Q threshold and say, well, now anyone in this blue area can access 10 acres of parks within that certain distance of them. And then increase up to 20 and say anyone who's there has 20 or less can access parks, has 20 or less acres of parks available in 200 meters. So we get this growing space, this filtration, where we can see as we increase this quality threshold of who has access to no parks, then a little bit of parks or less, or a medium amount of parks or less, you get this growing space. And so this defines a simplicial complex at each step, where we can consider the neighborhoods in Chicago that can access less than or equal to some number of acres of parks within that distance. And so this gives us a filtration for that increasing Q value, that increasing quality. And so this is one perspective we can think about, building a filtration based on that quality, where I fix some distance that I'm willing to walk and then look at how much quality different people have in different areas. But we could also flip the opposite. If I say I want to have access to 10 acres of parks, how far do I have to walk from where I live to be able to access that cumulatively within that radius of me? So in that sense, then we get this filtration where we have the neighborhoods in Chicago that can access Q acres of parks by walking more than or equal to M kilometers. So if you start by looking at the people who have to walk really far to access Q acres of parks, then decrease that distance a little bit, you're going to get more and more people added in as you increase or decrease that distance threshold. Sorry. So this gives us sort of two different perspectives of we can fix one parameter and vary the other, or fix the other parameter and vary the first, and see based on those, what are the holes in coverage or what's the topological shape. But we don't necessarily want to have to fix a certain value. Not everyone might be willing to walk the same number of kilometers from their house. So we want to combine these two ideas. So here we have this same sequence of the neighborhoods where within 200 meters, you have 0, 10, or 20 acres of parks nearby. And so we get these inclusions going in this direction. But then we can do the same thing where we have inclusions as R decreases. So each then vertical, each column here is fixed at, in this case, Q equals 0. So this is all of the people who within 2,000 meters have access to 0 acres of parks. Then this one is everyone who within 1,400 meters have access to 0 acres of parks, and then 800 meters, and so on. So we can decrease this distance in this direction to get a filtration, or increase the quality in this direction to get a filtration. And so this is what's called a bifiltration. In any direction, if we move to the right and down, you have an inclusion in that direction. So this collection of blocks will also be present in this collection of blocks and this collection of blocks, and so on. So bifiltrations are this generalization of a filtration where you have more than one parameter to think about. In this case, bifiltration is specifically 2 parameters. And so we have in one direction, one filtration, in one direction, the other filtration. This vertical, again, is that distance filtration, and horizontal here is the quality filtration, and then filling in all of the pieces in between. And so here we have this giant collection of spaces with inclusions between them, which in theory you can compute what's called multi-parameter persistent homology. But these are really hard to work with mathematically. So in single parameter persistent homology, what we've been talking about before, the persistence diagrams are a complete representation of what the topological shape is. There is no equivalent for multi-parameter persistence. You can't have a bifiltration and then output some equivalent to a persistence diagram. There's no complete invariant here. And so that makes them really hard to work with in terms of data because there's nothing to analyze after the fact that gives you all of the underlying information. There's lots of workarounds in terms of if you look at certain features of the bifiltration, but you can be missing information and it gets pretty tricky. So one thing that we thought about instead is let's just consider slices through this bifiltration. So we can consider, say, this sequence of horizontal slices or a sequence of vertical slices. And then in that case, you end up with one persistence diagram per slice. And the idea then becomes for each persistence diagram, can you identify what's happening across those slices? Can you match the topological features from one slice to the next slice to sort of capture information inspired by this multi-parameter persistence that isn't quite the same? And so we looked at this, and here we have 2 different persistence diagrams. So this is for 2 different slices, one corresponding to fix 1 kilometer and then filter on the quality, and the others fix 1.05 kilometers and filter on the quality. So not a huge huge difference in terms of that distance value. But trying to match up these persistence diagrams already becomes tricky. So we can probably guess that those circled on the left correspond to those circled on the right based on their general locations. And if there's one point that becomes a fairly easy match, we can check that the collection of blocks that's being represented by each of those points is roughly the same. But it becomes trickier when you have lots of things happening at one time. So you may have that one point on the left actually matches to 2 points on the right, where you have that, for some reason, the component isn't the same. And so one connected component then becomes two. And then how do you choose this matching? So this became sort of an infeasible attempt. But instead of trying to come up with some way to get this matching to work, we took a different direction. So if we look at, again, this is two of those slices from previous slides. And if we pick some neighborhood from this upper left, sublevel set. So if we take, say, this area here, this is actually the Chicago airport, but it's a big component, so it's easier to keep track of for visuals, but in theory, you can pick any of these small little connected components and see what happens. So we can track what happens to, say, the airport in this collection of filtration, collection of steps in the bifiltration. And so in this direction, we can see that it starts to grow, so it gets connected to more pieces here and more pieces in the next step. In the vertical direction, we can see that it's maybe still disconnected from some other pieces, but connects here. But then once you get to this point, it's sort of merged in with everything. There's no longer real use to saying that this whole area lacks access to parks because it's like half of the city. So in theory, we could look at what changes with the airport over all different slices and all parameter values, but we wanted to capture the idea that it's not the large regions that we're interested in, it's the smaller areas or medium-sized components that have poor access to these parks. Oops. So our approach works where we pick one small region from some parameter values where we would consider everyone there to be uncovered, or have poor access. So that example of if you have to walk 2 kilometers and you still can't access a single acre of parks, that's pretty bad. So if we take one of those small regions from that point, we can track the R and Q parameter values for which that feature is still small or still at a reasonable size where it's reasonable to think it's still uncovered. So this is a lot of different parameter values. It's small and hard to read, but we can see how generally things change here. So this is, again, the airport, and you can see it's growing pretty slowly until it starts expanding more rapidly. So you get this sort of small component, this localized feature, that then all of a sudden becomes like half the city of Chicago. So we want to look at these components where they're still small enough that we have localized information and we haven't just declared that the entire city of Chicago has poor access to parks. So in this case, we could look at these red regions or these red boxes as sort of the last in each row where the feature is still fairly small. And you can choose how to define fairly small. We chose a cutoff of the number of blocks in the component. And so at this point, we now have this collection of connected components. Oops, sorry. So we have this collection of steps and different pieces where we end up with these as our sort of final idea of what's the region that's uncovered. And one thing that we can note is that different initial components can still give us the same medium-sized component in the end. So if instead of picking the airport, I picked, there's a small, where is it? So there's this other small blob here. Rather than picking the airport, if I were to pick that one, I end up with these same final components in red here. And so this gives us a way of narrowing down. We don't necessarily just have to pick the airport and see what changes with the airport. We can look at all of those small little components and see some of them will end up giving us the same result. So then what we do is take the union of all of the smaller components that end up in the same medium-sized component. So at the top we have, it's disconnected, but as these go through the filtration, they both end up at the same final point here. And so we end up with this collection of spaces where we can take the union of all of those, and that gives us what we're calling our maximal component, or the union of all of those representatives right before they become too large, and whatever that means. So in blue here, that's the component from taking all of those unions, and on the right is the sort of range of acres and meters values for which that component isn't then merged with the entire city. So we're saying that this area has poor access to parks over that sort of tan colored collection of parameter values. And we can do this for every component that is born in that range of those like 9 images that I showed before. And we actually only end up with 7 distinct maximal components in the end. So that was one of them. These are the other 6, and they each sort of have different extents to which we would consider them uncovered. So some of them have are a smaller number of parameters before they merge with the bigger component, whereas some of them are isolated and disconnected for many different parameter values where we would consider it more isolated or disconnected from the rest of the city. And then if we color this component by some measurement of like how many of these parameter values do we consider it disconnected, this gives us a way to rank these components in terms of which ones are we might consider the most or least vulnerable. So all of these areas are going to be considered as having poor access to parks as compared to the rest of the city, but maybe this one in particular is particularly bad. So that would be an idea of where to put your newest park. And then we can even look within one of these components and try and look at the individual blocks and see when did that block join the medium size component. And so those that have been in the component for a long time would be the ones who've been uncovered for the most amount of time, or for the most parameter values. So here we have, in this one, we have some smaller collection of points where maybe that's our goal for where to put a new park or something like that. So this gives us a way to rank the connected components on their vulnerability, and then within a connected component to rank the neighborhoods in terms of their vulnerability and access to parks. Cool, so now I'm gonna change gears for a second, but before I do, are there any questions on this part or any clarification? And also wait until the end. I did just want to mention, so an undergraduate student of mine, Erin O'Neill, who is from UCLA, she worked on a related project, but looking at cooling centers in terms of studying vulnerability during extreme heat events. So this was part of her senior research project at UCLA, and we recently put it on archive. So if that's of interest to anyone, that's available. But now I want to make a slight detour into what I think is a really fun way of using these topological features to study social systems or things that are actually fairly relevant in our lives as mathematicians. So this was part of an REU this past summer. And the project I'm going to talk about was worked on by 3 undergraduate students, McKenna, Kelvin, and Ahora. And their goal was to, well, really they wanted to look at trends in terms of where undergraduate students end up going to graduate school to see if there's correlations or patterns in terms of these trajectories. That data is a lot harder to come by. So if you move forward a few career steps, we started looking at trends in the faculty hiring. So if you get your PhD from one institution and then you end up hired as a professor at the next institution, are there patterns or hierarchies in that process? And so are there schools that hire more often from one place than another or something along those lines? So this was their sort of initial idea, and they were able to use data from the Math Genealogy Project. So the Math Genealogy Project tells you, you report where you got your PhD from, and then once you have a student or a PhD student graduate from that university, you get that student added to your profile. So we can determine that where someone got their PhD, and then as a proxy for where they got hired, it's where do they graduate their students from. So we would assume that that's where they ended up getting hired for their tenure track or faculty job. And so one thing that they wanted to look at is patterns in terms of direction. So this is a directed process, right? I get my PhD at one institute and I get hired at another, and that's different than the reverse. And so they wanted to look at these cycles where if each vertex is a school, are there cases where I got my PhD here and I got hired here, and then someone else got their PhD here, got hired here, and you have this sort of full cycle of everyone has exchanged, all 3 of these schools have exchanged graduates. Probably more realistically, just in terms of sort of how we think faculty hiring works, it's typically thought that you get hired at or where you got your PhD, that sort of determines the quality of the school of where you can get a faculty job. This, of course, isn't always true, but it does seem that it would be more likely that maybe a student from here got hired here, a student from here got hired here, and a student from here then got hired here, where this might be considered sort of the top tier, the top ranking school. This is a more middle tier school, and this would be the lower tier school. Of course, this is a very much an oversimplification of the process, but we just wanted to look at these general trends of can we capture the difference between these cycle patterns. And what enables us to do this is to look at what's called a clique complex. So in terms of the filtration, we would add in a triangle only when you have this hierarchical pattern. Otherwise, this cycle would last forever. It would never fill in. So we can distinguish between the two. So they look at a weighted network in terms of where they weight this based on the weight of an edge from school A to school B is the fraction of hires at school B that got their PhD from school A plus the reverse direction. This is undirected. It gives you a sort of common strength without considering that hiring is directed. And they could look at the strongest connections. So this going from top to bottom is what would be considered the strongest connection at the top and the weakest or weaker connection at the bottom. And at the top here, this Howard University and University of Maryland College Park was sort of a special case. It turned out that Maryland, I think, hired like 8 faculty in the span of the time we were looking at, and something like 6 of them were from Howard. So that's a probably uncommon fraction that get hired at the same school. But the students also divided up what these strongest connections are if you isolate the data to only men or to only women. And so on the right, colored in green are connections where at least one side of the edge is what's considered a top tier school. They got this from some ranking on World News Report or something. So this is, yeah, everyone can have their own opinion in terms of what's a top ranking school, of course. But this is, here you can see that the men have some of these where at least one side is what's considered top ranking. And if we look at where both sides are top ranking, that consists of almost all of the strongest connections for men and only a few for women. So this is, of course, also a data issue if there are less women in math, so you're going to see less of these connections occurring. But they look at this filtration where if you start adding edges based on this strength, so the strongest connections get added first, then you can capture the holes in coverage here for the undirected version. For a directed version, then you can think about the edge as the fraction of schools, or the fraction of hires from school B that got their PhD from school A. And in both of these cases, using these different weights, you can look at the persistence diagrams. And so on the left here, this is if we considered everything to be undirected. And on the right is if we consider things to be directed. So on the left, a triangle gets added into your filtration if there are pairwise edges between all three schools. On the right, a triangle only gets added if you have this hierarchical pattern in your directed graph. So you have this clique. And we can see that they're very much the same. They're very similar here. And so it kind of indicated to us that this hiring is almost always happening in this hierarchical pattern. You're not seeing much of a difference when we add in this directed information because all of the cycles in the undirected version turn out to be this directed type once you apply this in the directed case. So this is still ongoing work and just a sort of fun undergraduate data analysis project at this point, but the students are going to continue to work and pursue this project and see if we can find other interesting trends and in this data. Okay, so that wraps up my sort of two different applications of topological data analysis for studying social systems. So we have found that TDA offers a very flexible framework for looking at resource coverage. You can include bifiltrations, you can look at distances in terms of travel time. It allows you a lot more flexibility than some of the more standard approaches. And this can be applied to lots of different applications. So you could consider coverage of schools or libraries or sort of the opposite of what might be considered a resource, what areas are overcrowded with landfills or highways or sources of pollution. So yeah, we think this offers an interesting framework for social systems, which is something TDA isn't often used for. So yeah, thank you. These are my references and I'm happy to take any questions.
All right, thank you. I'm gonna figure out how to click on some buttons here so I can thank you properly. You see Zoom changed on me, so react, there we go.